So hello everyone. I'm Dan from Personae Labs, and I'm the co-founder of Personae Labs. And I'm going to talk about client-side ZK for this presentation. And I won't go too deep into the technical details and only touch the high-level questions that exist in the space now that I believe are interesting questions. Um, okay, so for this presentation, I'll talk about these two things. First, the two paradigms to achieve fast proving through right field arithmetic. And the second one is interacting with smart contracts through generalized proofs. But first of all, what does client-side ZK even refer to? It turns out there are many domains that client-side ZK touches, from ZK rollups, so like private transfer rollups, and ZKML, and also things like ZKML, things like proving that you ran an inference model properly without revealing the witness for things like biometric recognition, and also for the primitive that we call credible nuance, which is a the definition the definition is the set of statements about the world, the global state that are nuanced, where nuance refers to the property that the underlying information on this statement can be kept private. And I'll share the link to this slides later, so you can. And there'll be many links in the slides, so you can go ahead and click the links and then see go deeper into, for example, credible nuance or other things that I talk about. And I believe the common denominator of the things client-side ZK refers to is their knowledge proving on a resource constrained device. So I think it'll be important to keep in mind that this is the problem that we're trying to solve when we talk about client-side ZK. And first of all, when talking about proving on a resource constrained device, an important property to consider is right field arithmetic. And but why is that? So oftentimes you want to prove some knowledge of a cryptographic key when making a statement in a zero knowledge proving system, such as like ECDSA keys of an Ethereum account, or a P256 key, which is embedded in mobile devices that I believe wallet developers are trying to utilize when building things like account abstraction wallets. And basically proving statement about a ECDSA signature, for example, on a BN254 curve, which is I think it's usually referred to as a ZK-friendly curve. You will need to do wrong field arithmetic, so the circle will be really large and the proving will be really slow. However, if you use the second Q curve, which is the curve that allows you to natively embed or natively encode and group elements of SecP curve. Using that curve, you don't have to do any round field arithmetic, so proving will be really fast. So yeah, this is the basic reason why right field arithmetic is important, because that will reduce the circuit size and allows you to allows the proving to be fast. But I guess we know that right field arithmetic is important, but how do we get right field arithmetic then? I believe there are two main paradigms that we know now. One is using or building a backward compatible proof system. For example, Spartan ECDSA, this is a work from Personae Labs, which allows you to, which is basically the implementation of the usage of SecQ curve that I just talked about. And the second paradigm is to attest to a ZK-friendly key from a non-ZK-friendly key. So for example, Sysmo, I believe, is using this paradigm. And I'll go through the details of these two paradigms later. But the important question here is, or an open question that we have now is, how should ZK app developers choose between these two paradigms? I won't provide a concrete answer to this question yet, but I think we can elaborate on the pros and cons and also the details of these paradigms. So more about the first paradigm, using or building a backward compatible proof system. So first of all, what makes a proof system backward compatible? There are a bunch of properties, but mainly a backward compatible proof system doesn't use FFTs, and there's no pairings, and there's no requirements for a cycle of the elliptic curve. So for example, Spartan, the underlying proof system of Spartan ECDSA that I briefly mentioned, doesn't require FFTs, doesn't require pairings, and also doesn't require a cycle of a curve. So it is a backward compatible proof system. And also EC Fry, which is a variant of Fry that uses elliptic curves to do use like utilize optic curves to like allow all fields to be able to generate Fry proofs. So EC Fry is also a backward compatible proof system, and things like Planck, Gross-16, and also for example Nova. Nova requires a cycle of the curves. So even though curves like popular curves like SecB or really SecB has a cycle, but the P256 curve, which is the curve that is which is used for the secure enclave of mobile devices, doesn't have a cycle, so it won't be able to leverage Nova, so that won't be a backward compatible situation. So this is the details of what I mean by backward compatible proof system. And on the second paradigm, attesting to zero knowledge ZK-friendly keys from non-ZK-friendly keys is to basically have a mapping between a non-ZK-friendly key like ECDSA keys to a ZK-friendly key in a smart contract, and user generate their ZK-friendly key and attest to that key using their non-ZK-friendly key, and then just prove with the ZK-friendly key. This is the second paradigm. And so what are the pros and cons of these two paradigms? The advantage of the first one, using backward compatible proof system, is you'll have a relatively simpler architecture compared to the second one. But the disadvantage is that you're restricted to the features of existing wallets. So because you're signing with like crypto wallets, you don't get nullifiers. And regarding the second paradigm, the advantage is that unlike the first one, you'll get more flexibility in the statements you can prove. Basically, you'll get nullifiers because you have control, or the app or you can directly generate proofs using from the private key, in the first paradigm, because private keys are embedded or are not accessible from interfaces, you can't do that. And the second disadvantage of the second paradigm is that as seen in the previous slide, there's this like mapping in the smart contract, and users need to go through a registration process, and also there needs to be an anonymity delay to preserve the anonymity of the user, because if you create a statement or submit a proof immediately after you register, then your public key and your statement might be related. Basically, if you have like a latest update on the registry, and also there's a proof that is submitted at a pretty similar timestamp, then those two can be related. So there you need to have some kind of anonymity delay. So it will require a relatively more complicated architecture. But yeah, but for now we don't have we don't have an opinion on which is better. And I think we have to explore both of these paradigms to understand them more. And yeah, since there's going to be many more changes to the identity stack of Ethereum as account abstraction and more L2s and L3s come out and people have more addresses, then we'll probably see a pretty different situation than we have now. So I think, yeah, for now we have these two paradigms, but as time goes on, I think we might see a different situation that might make sense to use one or the other. And on the second topic that I wanted to talk about today is interacting with smart contracts through zero knowledge proofs. And so first of all, why do we want to interact with smart contracts through zero knowledge proofs? And the purpose that I want to talk about is not about succinctness. And I want to emphasize the zero knowledge part of zero knowledge proofs. And the main reason is the ability to talk to smart contracts with credible nuance will unlock a new set of applications that can be built. This is the hypothesis, or this is the idea that I have. And more specifically, we see a lot of credible nuance that is privacy preserving membership proofs. So things like, so for example, you can prove that you own an NFT without revealing your address. That is a credible nuance, more specifically a privacy preserving membership proof. And with this new primitive, we believe there will be new set of applications that can be built. For example, like on-chain private voting is a pretty basic example. And asset transfers, obviously, and also, but also things like experimentation with governance. For instance, in relation to discounting that quadratic funding, which I believe Gitcoin and others are exploring. I think credible nuance and credible nuance will unlock these kind of experiments and new set of decentralized applications. So yeah, we want to explore what we can do with them, and how should we enable that by enabling interaction with smart contracts. So when talking to smart contracts, there are several considerations that we need to several things to consider. One is the proof size and verification complexity. So the proof size of the proof system and the verification complexity, and also the verification procedure, the compatibility of verification procedure with various chains, because smart contracts live on blockchains, L1, Ethereum, or any L2 chains. So we want to be able to verify them using the supported methods of those of their respective chains. And also we want to think about the scalability of verifications. So if we have many users, millions of users submitting proofs, generating proofs, can we able to scale the verification? Even though the verification of snarks are succinct, when you have many, scalability might become a problem, and it's more, and especially when it comes to client-side ZK and like that more compatible proof systems, the proofs can be pretty large, because you don't want to let the proof generators or the users with the resource constrained devices to do the heavy work to compress the proofs. You just want to let them make the statements or knowledge and not do the compression work. So the proofs could be large. So we also need to think about if those large proofs can be propagated properly, and also can it be scaled? And for now, as far as we know, there's no existing solution that provide convincing properties regarding the above considerations. And I won't go through why existing solutions doesn't provide these properties for in this presentation, but I will provide an example of a foundation of a proof system that might provide these properties. So yeah, what will a proof system satisfying the above look like? That is the question that we have and we want to answer. And before before talking more about the question and the answer, I want to talk about data availability and proof size. So for some or most zero knowledge applications, proofs don't need to be posted on L1 of L1, or its data availability layer doesn't have to be Ethereum L1, and off-chain data storage is sufficient. This is because the reason why you want to post data or post the entire proof, post data on chain is that you don't want sequencers to freeze or take hostage of your assets. But for ZK apps like private voting or even like verifying privacy preserving membership proofs, you don't need to have data available. The situation of data availability is different from asset transfers. So many applications should be okay with off-chain data storage. And if necessary, zero knowledge proofs can be, so if it's verified on a Validium, it still can interact with L1 smart contracts through L1, L2 bridges, or like if it lives it on L3, then it still can talk to L1 through bridges. So for zero knowledge applications that don't involve asset transfers, off-chain data storage, so verifying proofs on Validiums should be sufficient. So with that observation, for some zero knowledge applications that don't involve asset transfers, the proof size of a proof system doesn't affect the cost of verification. So the proof size of the proof system that we are using, it's okay to be large. So yeah, for some ZK apps, large proofs are okay. And with that insight, so we're exploring a Fry as a foundation to build a proof system that satisfies the properties that I talked about a while ago. Just to recall that properties is that we want, it's okay to have proofs, large proofs, and but we want to be able to be compatible with various chains. And we also want to be able to scale the verification. So like batching proofs of recursion will be nice. So with that in mind, when we see what Fry provides, the nice properties of Fry is that with EC Fry, it works with all finite fields. So you'll be able to do right field arithmetic for with any cryptographic keys, SecB or P256 or anything. And also there's no cryptographic component. So achieving compatibility with various chains, especially L2s, is likely simple because you only need to do hashing, and on L1 it'll be Jack, and in L2s it might be Poseidon or some like a ZK friendly hash function. So you don't have to deal with like if this L2 supports pairings or this up the curve operations or something. So yeah, achieving compatibility with various chains is likely simple. And also Fry provides a pretty simple batching method. So scale and verification is likely going to be pretty simple as well. If we want to, we can also do recursion. Fry provides a pretty fast recursion. So that might be an interesting direction to explore as well. But for now, at Personae Labs, we're prototyping a proof system called Spartan Fry, which uses the Spartan IOP with multilinear variants of Fry. So using multilinear polynomial commitment scheme based on Fry with the Spartan IOP to see if we can build a proof system that achieves the properties that we want. And to recap the two things that I talk about and in this entire presentation. So on the first part, so there are two ways to achieve right field arithmetic. One is to use or build a backward compatible proof system. And the second one is to attest to ZK-friendly keys from non-ZK-friendly keys. And the open question we have is that how should ZK app developers choose which paradigm to use? And the second thing that I talk about is about interacting with smart contracts through zero-knowledge proofs. And the open question we have, or the thing that we are exploring now, is a proof system tailored for ZK apps that rely on off-chain data storage. And that could be the key to unlocking this new primitive credible nuance. And Fry looks pretty suited as a foundation for such a proof system. And yes, that is all. Thank you for listening.
Cool, thanks, Dan. Is it okay if we open it up to questions now? So I can start with a question if that's okay. I wasn't sure. So like in the right field arithmetic discussion, I wasn't sure like how the backward compatible proof systems enable right field arithmetic. Like you gave a definition of backward compatible that was like no FFT and no pairings, and but how does that actually how does that give you the properties you want basically?
Right. So what we want to make backward, so what we're targeting is using curves that is used for managing cryptographic keys like Ethereum accounts. So Ethereum account is based on SecP, and the ECDC signature into a circuit. We want to have a circuit that can directly encode those keys without doing any like big end or round field arithmetic. So we want to base our proof system on a cycle of sec key, for example, like cycle or like a cycle of the sec p curve, which is a sec q curve. So we want to encode all the witness onto the scalar field of sec q. And the properties of SecQ is what I was talking about here. So SecQ the SecQ curve doesn't have a smooth multiplicative subgroup, so it can't do FFTs on the base field of SecQ, and also it doesn't support pairings. And so those two properties are missing from SecQ. So we can't use proof system that require those properties.
Got it. So when you say backwards compatible here, you're saying backwards compatible with the SecP like signature basically.
Yes, yeah. Exactly.
Got it. Okay. Cool. Okay, yeah, I thought it was like a more general backwards compatible notion, but it's just specific to this like SecP curve. Okay. Thank you.
Also SecP curve and maybe keys like P256 curves might also be interesting to make to like allow generating proofs with P256 because there are many keys that are embedded in like mobile phones. So that might be an interesting direction to explore as well. But SecP is for now the most interesting keys that we know.
Anyone else want to jump in with a question?
Yeah, I can ask. So I was curious if you've done any analysis on like how this approach, the new approach that you're talking about, sort of EC Fry with like a modified Spartan IOP, how that compares to just doing like wrong field arithmetic, or yeah, just like wrong field, and with using like a small field, like something like Goldilocks or even smaller, if you've done that kind of analysis, and also like yeah, circuit or VM approach, like error constraints.
Yeah, so that is a good question. We haven't, for now, we haven't explored the direction much. There are really like small circuits that use lookup tables to make wrong field arithmetic really efficient, and the footprint of circuits keep the footprint of the circuit small. That could provide a pretty decent or pretty fast prover time for in our setting as well. But for now, we have seen, for example, in Spartan ECDSA, we have seen a pretty successful fast proving in resource constraint devices. And Spartan ECDSA is taking the approach of right field arithmetic by building a backward compatible proof system. So we're trying to expand the direction. But there's definitely a possibility that using really small fields, and yeah, maybe using constraint system like air could provide a pretty fast proof system. Yeah, another thing I think it will be interesting to mention is that since we want to make the proving keys as small as possible as well, and also keep the proving keys to be small as possible, because every time a user wants to generate a proof in the browser or in their mobile phone, they likely have to download the private key and the circuit as well. So I guess we really haven't explored the direction, but there'll be there'll probably be a bunch of unknowns when it comes to like actually running these systems in mobile phones and browsers. So it will be an interesting direction to explore. But for now, we're just expanding on the things that we know that works.
Thanks. Yep.
I was gonna ask a question about the like Validium part. Like, do you have like Validiums in mind, and how a system like how a system would actually work with posting a proof on like off-chain DA and being able to verify on-chain?
For now, we haven't. I'm not sure if there are Validiums that I'm not sure if there are Validiums that are currently operational. They might be. But I think a good like analogy or a good way of thinking about this is you're just doing a proof composition, but you're not like usually proof composition in for example, in a recursion setting, you might have Nova or Halo 2 that does the recursion part, and there's a final ZK snark that that compress the entire thing into a really small proof that can be verified on Ethereum. So that's so the last part is proof composition. But in our case, that we're just using Validiums and the provers running the Validium system as a system to compress our proofs, or like as a part that does the proof composition. So in theory, we don't have to use Validiums. We just need to have a way to compress the proofs in compress the proofs so that the final proof is verifiable on Ethereum. But I think using Validiums, operation Validiums will be simpler and will be easier. So I think like proof composition and using Validiums is basically the same thing, or the idea is basically the same thing. So that might be a good way to think about it.
So okay, so just to be clear, like Validium is when you post your data off chain, but use a ZK proof to settle to some on-chain.
Yeah.
And so you're saying that like ZK proof of like settlement is in a way like a compression of the off-chain posted ZK proofs.
Yeah, yes. Exactly.
I see. Yeah, I think I haven't heard of like that many projects going Validium, although I mean there are ideas of like layer 3 on top of layer 2's Validiums, but I don't know. Maybe like I think maybe ZK Porter, maybe from
Yeah.
ZSync. But
ZK Porter and I think Starknet and yeah, other layer
yeah,
twos have volumes as well.
yeah. Okay, cool. Um, cool. And then like what's the last question I wanted to ask was like, can you give a like what's your canonical like example of a nuance, like this nuance statement that you have?
Yeah, so I guess most of credible nuance, most of this nuance statements that we see now are membership proofs. So things like ownership of you prove that you own an NFT without revealing the address of your Ethereum address, those kind of stuff. And I'm not sure if I have like a canonical obligation in mind, but things like at least things like membership proofs for quadratic funding could be a really interesting like mechanism to explore. Where in like quadratic funding, I think a CoinExpo is exploring this idea of using membership proofs to prove your like how far are you from like other funders. So how likely are you to collide to collude, and you prove probability by submitting a membership proof, but you obviously want to preserve privacy, so you want to use privacy preserving membership proofs. So that will be an interesting place to see membership proofs, and that will be a pretty interesting and new mechanism. Yeah, that would like definitely would like to see be experimented.
Cool. All right. If there are no more questions, then maybe we could call it there. Thanks a lot, Dan. I appreciate your time. All right. Bye, everybody.